Welcome to Terrible Lizards, a podcast about dinosaurs with Dr. David Hone and Izzy Lawrence. Planes, trains and automobiles. Pterosaurs didn't use any of them, but how did they get about? They didn't just fly. Could they swim? Could they run? Dr. David Hone and Izzy Lawrence are here to tell you all. Welcome to Terrible Lizards, everybody. It is awesome times. We are talking about flappy flaps, and we're also going to talk about flappy flaps walkies, and also dancey dancies, and also head boppy boppies, I assume, because we're talking about pterosaurs in motion.
Yes, but you've slightly thrown me with that introduction of usual Izzy nonsense.
I think that was an adorable introduction to pterosaurs in motion, because Pterosaurs in Motion does sound like the worst film ever.
Oh, I don't know. There was a famously unmade Hammer horror picture for which the poster exists, but they never made the film, which was Pterodactyls versus Zeppelin. Ooh. And I wish that existed. And yeah, it's a classic old World War I era Zeppelin with all these
starring Peter Cushing,
Ramforinkoids flying around it. Yeah. Like, yeah, we wanted to see that. Oh, we could definitely do a terrible Pterosaurs on film episode at some point. There's a lot of them. But including, I think it's called Pterodactyl, starring Ice Cube, who is not the kind of classically trained actor that one might expect of a high-quality pterosaur movie production. But anyway, talk about pterosaurs in motion. So, obviously, pterosaurs can fly. Yes. I think we're happy with that bit. Yes. But it's worth talking about how they flew and how well they flew.
Okay.
But also kind of want to talk about pterosaurs on the ground. There's a lot of myths and misconceptions about that, and our understanding of that has changed. Even very recently, down to the last year or two, we've had some new information on that. And then even pterosaurs in water, which again has been massively misinterpreted.
Can we do pterosaurs on a bicycle?
There's not really 3 episodes to be got out of that. But no, we're not doing pterosaurs on bicycles for some very obvious reasons. But we'll start with the obvious one. Did pterosaurs fly? Yes, and more specifically, they were true powered flyers. So they are not passive gliders or soarers who are relying on jumping from height or relying from rising air or relying on wind or anything like this.
Or
every
cliffs.
Pterosaur that we know of, but that's height.
No, it's updraft too, to be fair. It is updraft too.
Oh, true. Yeah. All pterosaurs that we know of, right the way up to the biggest Agdarchids, the 10-metre wingspan jobs, were true powered flyers. They could take off from the ground and flap and gain height and fly around. And that might sound self-evident, but at least at various times, various big pterosaurs have been said, oh, they couldn't fly properly, or they must have been too heavy, or maybe they were flightless when they were adult. There's no reason to think that on any of them. So let's get that out of the way. Secondly, they were probably very good flyers. We've muttered about this before, I'm sure, and without delving into terrestrial side of things too much before we get there, but pterosaurs would have taken off like bats. Namely, they're jumping with all 4 limbs, and in particular, they're launching with their forelimbs, their wings, which have all the flight muscles on them.
You can't go and say things like pterosaurs are taking off like bats, because people think that bats always take off from upside down.
Dropping out of a tree. Yes.
No, underneath a cave. That is how bats take off. Don't tell me that bats can take off from the floor. That's weird.
Some are very good at it. So there's a lovely little thing called Mr. Kiner from New Zealand who hunts on the ground, who runs around on the ground hunting insects. Vampires are extremely terrestrial adept. I'm sure I've mentioned this before. There's videos of vampires running on treadmills. They gallop like horses.
Christopher Lee has never been on a treadmill.
Vampires properly gallop, and they also have this, ballistic launch where they take off in one, not even a step, they basically crouch and launch. And that's what pterosaurs are doing.
How can somebody get a PhD funding thing to put vampire bats on treadmills, and yet we can't get more money for very important dinosaur research?
I know. You think that's bad? There's videos of shrimp on treadmills. No, I'm not kidding. It's very cute, I have to admit. But we're getting off topic. So pterosaurs, this is actually kind of important because there's actually an idea which is still knocking around, though it needs to die, that birds basically outcompeted pterosaurs, and where birds got going in the Jurassic and into the early Cretaceous, that led to the fall off in pterosaurs. It almost certainly didn't, and even if it did, it wouldn't be to do with birds being better flyers, which is what's often commonly stated, because birds were almost certainly not as good flyers as pterosaurs.
We can't even decide if Archaeopteryx could fly.
Well, that, but even the later ones. And this is in part because birds are fundamentally bipeds, and when they launch, they jump with their hind legs and then flap with their wings, which means that their legs are actually really big and muscly, and their only real job is to walk around on the ground and jump. And that's a whole lot of extra weight, basically, that they've got to then carry around when they're trying to fly.
All that junk inside their trunk, and they've got tails, heavy tails.
Well, some of the Ramforinkoids did, but still, this is going to limit them, and birds don't get to be as pneumatic as pterosaurs did, and so these are at least part of the reasons that pterosaurs got bigger than birds. But it also means that on average, for two very similarly sized and shaped birds, and pterosaurs of course don't quite line up already, the pterosaur was probably on average the better flyer. So let's get rid of this pterosaurs couldn't fly very well or birds were better flyers, because it's absolute nonsense.
I don't know if you've seen a swan flying, but they're rubbish.
One factor actually when birds start getting big is feather weight. Swans are something like 20% feathers. They have an awful lot of feathers, and particularly their wing feathers, and that weighs quite a lot. More, I am sure, than a wing membrane would have done. So you also imagine that bigger and bigger birds are rather heavier, again, than a comparable pterosaur would need to be.
But we talked on the previous episode a little bit about their potential floofiness.
Yes, but these are single, simple filaments. They're going to be much more like our hair or the down you get on baby chicks and things like this than anything else. They don't have a shaft. They don't have any complex arrangement. What is covering pterosaurs might be at some level a true feather, but they're not going to be feathered like adult birds. They're going to be feathered like baby chicks. And as I think we said, the wing membrane probably didn't have feathers on it, so there's filaments on it. So there's nothing in the wing. What they're flying with is mostly that giant wing. Their fourth finger, remember? So they have three free fingers, and then it's the long fourth finger and no fifth finger is making up this giant spar of wing, and the wing membrane attaches to that and goes down in some way, shape or form, probably to the ankle. So it will come in along parallel and then mostly would probably sweep down at a bit of an arc and meet the ankle. That's been a huge subject of contention for years, and I think most people thought the ankle attachment was probably the correct one. People have suggested the knee, the thigh, and even the hip. Briefly, it was suggested that it might attach like across the back and into the tail, though that got ditched again very quickly. But yeah, it was a paper I wrote with Dino Fry and our then PhD student Ross Elgin. Ross was the first author on this, where we documented basically all the known attachment points for pterosaurs. And what you find is on the rare occasions where you get properly complete wings that haven't been torn or squidged or rolled up or folded over, they either attach to the ankle or they attach somewhere pretty close to the ankle, like mid-lower leg. And given that these have almost all of them shrunk, because they'd be very elasticated structures which are going to shrink when the animal dies and dries out and other things like this, you're almost certainly not seeing the full extent of it. And so, yeah, for every good specimen we have, from the earliest pterosaurs to the last pterosaurs, you see an ankle attachment or something close to it. So again, much like our filaments that we talked about last week, it's reasonable to infer from that an ankle attachment was the default. But that's not the same as necessarily it had a really broad wing. So I think some people then think that means, so if I'm drawing my pterosaur, I stretch the wings out, I stretch the legs out, and I just draw a straight line from one to the other. No, it doesn't work like that. Things like Pteranodon, which is a very oceanic animal, I'm sure had a relatively narrow wing for most of its length. So, the trailing edge, the posterior part of that wing, track alongside the wing bones at the front, and then when it gets close to the body, it would kind of sweep down in an arc. So it'd be almost kind of L-shaped trailing edge.
Because that's what you see in albatross and things. Narrow wings.
Yeah, so there's two things that basically tell you how an animal flies, or at least a vertebrate flies. So I was going to say, to a lesser extent, it's true of planes as well. They have some other issues going on. But one of them is wing shape and what's called aspect ratio. So how long the wing is side to side versus how wide it is front to back. So that's aspect ratio. So a high aspect ratio is albatross, very long thin wings, or glider aircraft that people fly around in. Low aspect ratio wings are almost square.
Blue tit.
They're as wide as they are long. So yeah, things like blue tits, buzzards, magpies are heading down towards that area, those sort of things. So that gives you one type of performance, and then the other one is what's called wing loading, and that is the area of your wing divided by your mass. So you could have a very long thin wing, but also be very light. But you could have a very long thin wing and actually be pretty heavy. And so those two factors between them for a powered flying animal really explain an awful lot of your flight capacity, and whether you're good at turning, or whether you're good at going long distances, or whether you're good at catching lots of lift, or whether you're good at flying in narrow spaces, technically cluttered environments. So things like blue tits and magpies, they have relatively short wings. So that's good at getting through gaps when you're flying between twigs and branches and leaves when you're hanging around in forests. That's probably not a good idea if you're an albatross, who's much more interested in making very sharp turns to catch the wind when it's out in the middle of the Antarctic Ocean. So we'd love to be able to do that for pterosaurs, only of course with the obvious problems that it's difficult to reconstruct their wings very well, so we don't really know quite what aspect ratio they've got, and it's difficult to estimate their mass very well, so we don't know how heavy they are and what their wing loading is. So apart from not knowing their aspect ratio or their wing loading, we have a great idea of how they were flying. We can obviously do a whole bunch of estimates for this, but you end up in some weird bits of wing space for some estimates that suggest that we haven't got it right and don't really match what we think. But at least some of them, things like Pteranodon, our estimates put it to be flying something like an albatross, which, given that we think it's living something like an albatross, is probably about right. So for at least some of them, we've got a fair idea. So we talked about preservation a bit last week. So again, pterosaurs don't preserve very well at all. We have lots of pterosaurs who are preserved in marine sediments from lagoonal systems or, coastlines and estuaries and things like this, where they look like they're probably living in terrestrial environments, but we found them in the sea. So is that because they did live in the terrestrial environment and we found them in the sea because they died and the river washed them down, or they're close enough to the coastline that sometimes they're out there and then that's where they died? Or were they actually living on the coastline and that's why we keep finding them there, and we've completely misinterpreted their biology and their coastal or marine animals and we think they live inland? Don't know.
Yeah. Could be like seagulls and do both.
Or are they generalists who are capable of doing both things? I mean, there's at least a few which are the opposite. So Liaoning and the Ischian formation, which comes back again and again and again because it's Microraptor and Psittacosaurus and exceptional preservation and yada yada yada. Mainland China, it's well inland, and it was well inland at the time that it was laid down in the early Cretaceous. And we've got some big ornithocheirid pterosaurs, and ornithocheirids are one of these, like, we think of them as like an oceanic albatross-like animal, and they're well inland. So
maybe they were lost.
Well, they're in good enough numbers that that's certainly not the case. But are they very gull-like? And therefore, actually, if there's a nice big body of water well inland, that doesn't really bother them? Or were they much more generalist than we thought they are? And maybe they're not as good in the oceans? Or as usual, for terrible lizards in general, and pterosaurs in particular, we don't really know. Going back, wing membrane. So that's the big wing membrane. But they have two others. So the correct term for that is the brachiopatagium, so arm membrane, basically. But we have the propatagium, which is a little front one, and that sits in kind of the crook of the elbow. So if you can imagine just holding your arms, so put your elbows kind of pointing down and then your hands kind of pointing up, you end up with a bit of a...
Like you're surrendering.
Yes, pretty much. You end up with a bit of a V in the elbow, and the propatagium sat in that gap.
So between your shoulders and your wrists.
Basically, yes.
That's gonna stretch out quite a lot and you open your wings up.
Again, so these wings, we'll get onto wing structure in a bit, but they're very, very elastic. The interesting thing about the propatagium is it's supported by a very modified and weird wrist bone called the pteroid. So the wingoid, almost literally. And in the early pterosaurs, it's a little nub. It's like a little spike. And in the later pterosaurs, it's often a very long, thin rod that's even L-shaped. And this sits somewhat along the leading edge, so the front edge of the pteroid. And there's a whole bunch of pterosaur literature about exactly where the pteroid goes and exactly what angles it can have and exactly what it can do. For a while, there was a suggestion that the pteroid pointed forward, so like a little machine gun sticking forwards, which would have given you a huge propatagium. That's, I think, entirely correctly fallen out of favour. I always had problems with it. I think a lot of people did, and it wasn't a big surprise when it turned out to be incorrect. But certainly the pteroid is there to support that little front wing. The pteroid is almost certainly motile to a fair degree. which allows that to be its own kind of little front flap, like you get on some aircraft that if you push it down, it will change your wing shape. If you push it up, it will change your wing shape. And of course, being bony, it would help stiffen the leading edge. So that's the first thing that they've got, which is really quite a neat little feature, which will change their wings. And then the second one, or the second bonus membrane, therefore the third membrane, is the cruropatagium or uropatagium, which goes between the back legs.
Nice.
And this is really rarely preserved. We've got like half a dozen of them. They're extraordinarily rare, which makes me think they're very, very thin and therefore don't preserve very well. And we're not exactly sure quite where they're going. I am pretty convinced that they attached physically to the tail, but that is a big question. Is it like joining the hind legs and not the tail, or are they all three integrated as a whole?
If you're not joining the tail, you're going to get, I would suggest, I mean, I'm just thinking about their toilet habits and where things are going to...
Yeah, where would it go? I mean...
It'd have to join the tail at the very base of the tail, at least, surely.
Yeah, yes, you would think that you would have to have tail membrane attachment cloaca.
Yeah, rather than a sort of like sandwich cloaca with, unless that helped them laying eggs, because they could lower the eggs down on a sort of like, you know, emergency exit in an aeroplane with the, you know, you've got nice bouncy slides, but it would be a bit smelly.
Yeah. So in the early pterosaurs, in our non-pterodactyloids, they actually have this, people may remember, a large fifth toe, so a very long fifth toe, so the little toe equivalent, and the wing, the uropatagium is attached to that. So it would basically go, if you look at our pterosaur kind of top down, if we splayed it out on a slab as if it's been run over, as of course most of them look like in the fossil record, it would be a bit of a U or a V shape, basically going from the tip of one fifth toe to the tip of the other fifth toe, and fill in like most of the space between the legs, and I think attaching to the tail in the midline. And if anyone wants to know why I think it attaches to the tail in the midline, there is one specimen specifically that shows this. It's a specimen of Sordes, which is one of the very rare pterosaurs with filaments preserved. Sordes is a lovely little thing from Kazakhstan, and one of the specimens of Sordes, the uropatagium is preserved almost perfectly. It's by far and away the best preserved uropatagium for any pterosaur. And you can see that its trailing edge is basically a fairly sharp V shape. So it kind of goes up, and in about the midline of the body, it turns a very sharp, like 90-degree angle and goes back down. Now, the tail is off to one side, but we do know from some other pterosaurs where things like this have happened, and a big sheet like a membrane sticks very firmly to sediment, and then later on other bones can move. We've seen that for other stuff, particularly from Brazil. So just because the tail's moved doesn't mean that it didn't attach to the uropatagium originally. And the reason I think that it must have done is that very sharp point. If the tail had never been integrated with that, then you've got just a loose sheet of membrane, and even if it's got some kind of tendon or elastic ligament or something like that, you'd expect that to be a U shape. It can't go to a point if it's not attached to something that's a point that it could pull on normally in life. And relaxed, it would just go floppy. And it's not. It's a sharp V.
Was this a male?
Don't know.
And if it were a male, could it attach to that?
Attach to something else. I don't think so. But it means we've got this really quite big sheet of membrane between the hind legs for non-pterodactyloids. And that will become relevant again when we start talking about them on the ground. In the pterodactyloids, that fifth toe has all but vanished, and it's a little nub. And the tail has reduced massively in most of them. And now we think it's more or less just like a little sheet of membrane going from that fifth toe up the inside of the leg, kind of in the crux of the back of the knee, and then finishing, at the base of the tail and somewhere around the cloaca. So they now basically have a little strip of membrane down each side of the back legs, and they don't have this big sheet all the way across the back. So it's a pretty profound change in the arrangement of their wings.
Presumably, I mean, we've already talked about it with Microraptor and stuff, but having 4 wings is better than having 2.
Well, this is effectively one continuous wing.
Yeah.
So what you've got in the pterodactyloids is that they're split much more into 2 in terms of things like airflow. So, of course, for flapping animals, it's all about airflow and lift and power delivery, and that all gets very complicated very, very quickly. For these guys, at least, it's clearly having some effect on them. My general suspicion is that you've basically basically got a bit of a trade-off whereby having the Europatagium and the tail does give you some more lift and maybe gives you a bit more control, but then it's also coming at the expense of weight, particularly for the tail. And so if you can get rid of that, maybe that trade-off is actually about even. You know, the extra lift and efficiency you've lost is balanced by the extra weight that you had saved, and now you don't have to lug around all the time. I don't think anyone really knows. Working out the flight performance of even living birds and bats is an absolute nightmare. Guess what? We haven't got very far for doing it with pterosaurs. But it is worth saying, actually, that for bats at least, there's a lot of variation in there. They have an equivalent Europatagium in bats, and they do all kinds of interesting things. They have big sheets, they have split ones, they have ones that articulate with the tail and ones that don't. There's a group called free-tailed bats, because the bat tail isn't integrated with the leg membrane. So certainly there are lots of possibilities, and they don't necessarily cripple your flight characteristics or give you such a massive bonus that you outcompete everything and you're the only group left. There's a bunch of opportunities and options out there which still seem to work fine.
Bats seem to, though, I mean, from what I know, bats, which isn't very much, they're predators who tend to catch things mid-flight. So
We're not fruit bats, though.
We're not fruit bats, no, but they're not. They're flying foxes. They're not
yes.
bats.
They are
bats. They don't have it, do they? A membrane between their legs, do they? I don't think they do.
I think they've got them, off the top of my head, I'm going to say they have a more pterodactyloid condition. I'm pretty sure they have a leg membrane, but I think it's narrow and goes up the inside to the tail. I'm pretty sure you get the silhouette photos. Hang on. I don't think we've done this before live. We'll do it live.
Okay, we're doing this live. We're looking up fruit bats' rear ends. Here we go. This is going to damage your Google.
They've got exactly what I said. So they've got a little spar and it's coming up to the base, but they don't have a big long tail and a membrane integrated with that.
They've got very cute
from the photos
faces because they've still got eyes, which is why I quite like them.
Yes. Well, I believe all bats have eyes.
I know, but they've got big eyes that look at you and go, nom, 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 gooseberries. There's no evidence, I presume, of vegetarian. Sorry, just because we talked about fruit bats, I don't. Are there any evidence of vegetarian pterosaurs?
So there's the tapiarids, which are one of these groups actually, which we keep finding them in marine sediments, but we think they're quite probably terrestrial, and those are often interpreted as nut and seed and fruit eaters. They do have beaks that are somewhat analogous to parrots. There is something to support that. But yes, the rest of them are insectivorous, predatory, piscivorous type things.
So they would need that, if they're insectivorous particularly, they would need the aerodynamic ability and that acrobatic skill.
Yeah, you're going to want to be able to fly. I mean, yes, there's always trade-offs. If you're a very big, heavy thing that's trying to be more of a turkey or more of a ground hornbill or something like that, where you're spending most of your time on the ground and occasionally you just need to flap to get away from a predator or get somewhere you particularly want to go to. Yeah, that you may not need to be particularly agile, just capable of getting into the air and moving about. But for an awful lot of them, catching stuff on the wing was probably really important, and therefore they were highly manoeuvrable and good at doing that.
Cool.
And this is the next thing, which has tied us nicely back in. Well done. With just what they're capable of doing. So the wing membrane, we'd known for a very long time that the main wing membrane, the Brachiopotagium, has these stiffening fibres in it called actinofibrils. They're not present in the Propotagium, and they're not present in the Europotagium, which is probably why those don't preserve very well. And they're more concentrated at the tip of the wing, and as you get close to the body, after about the elbow, there are none left. And these are really fine. These are like sub-millimetre, even in very, very big pterosaurs, because the fibres, unsurprisingly, preserve quite well because they're very stiff and solid. And so you'll often see either paleo art or even some of the better models actually put these in. And they put these little grooves on the wing. It's like, you're never going to see them. Like, this thing is like 1/5 of a millimetre in diameter, and you've scratched it onto a model of Quetzalcoatlus that is got a 10-centimetre wingspan in the toy. That they're not showing up at that scale. And they're probably embedded in the wing, like in the tissue. So you wouldn't see them anyway because they're not actually external. But we didn't know much more than this for a very long time. And then we talked about this one in the last series. The dark wing specimen of Ramforinkus turned up, which has these extraordinarily well-preserved wings. And when you look at them under UV light, and it was Helmut Tischlinger, who I mentioned last week, who did this initial work, you can see the multiple tissue layers in the wing of the dark wing. And we can see that that they basically have three major layers. They have the actinofibrils at the bottom, they have a blood vessel layer, and now I'm trying to remember if it's on top or in the middle, but it doesn't particularly matter.
Jam sandwich in the middle.
There's what's called a muscle fascia layer. In other words, it's like a sheet of muscle. So not like a block like we have, that moves your arms or your jaw or anything like that, but just like it's just like a sheet of little fibers. And that means that, in theory at least, it could probably, under control, contract or relax any bits of muscle in the wing that it wanted to.
Nice.
Yeah, you've basically got active wing warping under neurological control across the wing.
And bats can't do that, can they? It's just skin with bats.
What bats will do is, so their wing membrane is highly elastic, but it's spread under tension under those fingers. And then what they're doing, of course, is contracting or moving the individual fingers to change the wing membrane. Pterosaurs are not able to do that when all they've got is this leading edge spar of bone, but they've got general support for it from the actinofibrils, and then the capacity to, again, tension or relax different bits of the wing.
I'm trying to think, is it a bit like an upper lip? Because that isn't obviously contracted. I'm just trying to think of a bit of a human that would be.
That's probably a bit more, yeah. I mean, our lips are really composed of lots of little blocks of muscle, but it would respond more like that, where you've got an awful lot of options for what you want to do. On top of that, there's a suggestion. This is based off I think it's based off one of the Brazilian ones, but I can't remember. There's definitely some like loose, maybe that's an air sac. So remember, pterosaurs, air sacs, pneumatic, blah. There's a suggestion that there are some air sacs in the wing as well.
That would be amazing.
Particularly close to the body, obviously, and just kind of around the elbow and upper arm. There's some ifs here. If they had air sacs, and if those are under control, which at least some air sacs almost certainly are, they are extensions of the lungs after all. You just need some kind of valve to let the air in or out. You might be able to puff them up and reduce them as well. So they've got the obvious things, they have got wings, they've got joints, they can control they can extend and retract the arm, and they can rotate the wrist a bit, and they can fold the finger a bit, and obviously lift them up and down. All of that is going to affect airflow. Then they got their pteroid moving, then they've got their Europatagium moving, because of course they can move the legs or move the toe, and probably move the tail as well. And then the main wing itself has probably got active wing warping through muscle contraction, and potentially also changing the shape and camber and the lift through changing air sacs as well. These are extraordinarily complex and technical animals, and I know you're desperate to make a joke, but I'm going to talk about how brilliant pterosaurs are first before I run out of air. Your turn.
I was going to say, imagine, though, how useful it would be if you're stuck on the water and you can take a big gulp of air, puff up your wings to help them stay buoyant, and then flap away because you've got air sacs in your...
That's not really going to make any... They're so pneumatic already. A bit more air in your wings is not going to make a difference between you.
It might help.
Floating or not.
I just like the idea of them having built-in life vests.
So pterosaurs were very, very good at flying and had, and actually another thing, so there's wonderful study done by Larry Whitmer and colleagues in 2005, something like that, 2007, where they were able to get a 3D scan of a couple of pterosaur skulls. So obviously we talked about brain cases and getting into the brains of dinosaurs at times. Pterosaurs, much less well preserved, much harder to do. But they managed to get a couple of pterosaurs done. Ramforinkus and one of the ornithochirids, I think it was Anhangera, and were able to show that both of these have an part of the brain called the flocculus, which is greatly enlarged and comparable to what we see in birds. And the flocculus is the bit of the brain that basically processes where you are in space. And if you walk around on the ground, we don't need a very big one.
I've got a tiny one. I bump into stuff all the time.
We're not climbing very much. We're not swinging around very much. We're not flying through the air very much. Our flocculus is tiny. Birds, it's huge. Particularly acrobatic birds, it's bigger. Pterosaurs, it's big and comparable to better flying birds.
I like it's called a flocculus because it makes you think of flying in a flock and not hitting each other.
Yes, a murmuration.
Yeah, of starling. There's a starling nest, by the way, in Waitrose's roof. I'm not going to tell them about it. It's good. Anyway.
Now there's an aside. But yeah, pterosaurs, really, really, really good at flying.
Okay.
And again, that sounds a bit trite, but against all of this, they could barely take off, they're reliant on cliffs, and you still see that surviving. No, boy, were they good. And again, there's no reason to think that they weren't, on average, better than comparably sized or built or wing performance birds.
No running up to take off.
Yeah, no need for a run up for takeoff. Standing jump, which we've kind of already talked about.
Press up is a standing press up day.
Yeah, pretty much. And then this, basically a takeoff stroke directly into the ground is more or less what they're doing, and then launching themselves off as a result. We'll talk about swimming and water in a bit, but some calculations have been done to suggest that actually they take off similarly from water. Most of them could do it in one go, and even the ones that didn't could do something equivalent to what we see in swans and geese, where they kind of run along the surface, building up speed as they flap. Pterosaurs doing that, but the wings impacting off the surface to get them off, and so they do like 3 or 4 flaps into the water as they move forward. But all pterosaurs appear to be perfectly capable of taking off from the ground, or even taking off straight from water. Again, takeoff not an issue, and again, even for the biggest ones, when you see turkeys and pigeons, well, actually no, pigeons are good takeoff, they just make a hell of a clatter. But things like turkeys, and particularly things like swans and geese that like need a big run up, or stuff like condors, which apparently you can catch by getting them into a wall.
Okay.
Do you know this one?
What?
So
I don't tend to catch many condors, to be fair.
Supposedly, the way various peoples in the Andes who, have a big tradition with condors, and one of the big things they do for a festival is that they like they feed a condor up and then release it as a kind of what's the word I'm looking for?
Like we might with a dove,
right? And so, but first you got to catch a condor, which normally like nest in canyons on cliffs and are massive birds. And apparently the way to do this is to build a small wall like that's only a metre high or so in an area about 10-15 metres across, and then put a dead sheep in it. And then the condors fly down and go, ooh, dead sheep, and eat as much as they want. And then they're really fat and heavy, and they need such a big run up to take off that they're then trapped inside the little wall, and you basically just walk in and pick them up. So pterosaurs wouldn't do that.
No, can't touch a pterosaur that way. Good point.
Yes. And that kind of brings us to pterosaurs on the ground. Now, here we do have a big split. Everyone's always been happy with the idea that the pterodactyloids are pretty good on the ground. It makes a lot of sense. They've got rid of that uropatagium, so they no longer have their legs all stuck together. Because if you think about it, for a non-pterodactyloid, so you've got that wing membrane that attaches your left arm to your left ankle, and then the uropatagium attaching your left ankle to your right ankle, and then your other brachipatagium attaching your right ankle to your right arm. And suddenly you're all stuck together. And this stuff might be very highly elastic, but walking around with all of your hands and feet tied to each other is not a great arrangement. And then you've got quite a long bony tail as well. Remember, they've got relatively short legs. They've also got their 5th toe tied up in all of this as well. You can see why they might not do very well on the ground. We'll get to that in a minute. But for the pterodactyloids, at least, they obviously don't have that. Yes, the left leg and arm and right leg and arm are stuck together, but that's it. And that shouldn't be too bad for them. And yeah, we have loads of pterosaur footprints. They're almost all in the Cretaceous. Or the late Jurassic and on, I should say. And when do pterodactyloids turn up? In the late Jurassic. So as soon as we get rid of the uropatagium, or at least a big uropatagium in the tail, suddenly we get pterosaur footprints everywhere. So it kind of looks like if you're going to want to walk around on the ground effectively,
don't tie your feet together.
Don't tie your legs together, as well as tying your arms to your legs. And yeah, so there's a site in southern France called Craysac, I'm probably not pronouncing that right. It's like a field of pterosaur tracks, and that's how you get these probing marks as well that I talked about last week and stuff like this. And they're absolutely everywhere, and there's a bunch of these in various places. When you get to some of the really big pterosaurs, the Asdarchids, we have some big footprints in Korea, we have some big footprints in Israel, I think it is, and a few other places.
And you can tell these are pterosaur footprints simply because it's the 3-fingery type with
so they're so obviously weird. So first of all, they've got plantigrade feet. They have have feet rather like ours. They're walking on the whole sole of the feet and then the toes, and they have 4 toes, because remember, either the 5th toe is holding up that membrane or the 5th toe is really tiny, so you're going to get 4 complete toes, a big flat foot with 4 toes. And then their fingers are much more solid, they're bigger and more robust with big claws compared to the feet, and then 3 just fingertips, well, fingers with no base, on the ground at the front, pointing sideways and backwards. So...
Oh, bless, they're doing that. They're going...
They're doing that. I'm sure that will show up well on audio. But yes, if you basically put your elbows to your well, not hips, but...
If you imagine you're doing a press-up, but just turn your hands the wrong way round.
And imagine doing a press-up, and then turn your hand sideways. So your index finger is pointing sideways, out to the side. Your middle finger is pointing at 45 degrees back, and your ring finger, because of course we got the wrong one, would be pointing straight back. So they're really, really distinctive tracks. It's very, very easy to see when a pterodactyloid has been walking around.
It does mean that in my head they're walking a bit like Stan Laurel and Oliver Hardy. They've got that sort of like Charlie Chaplin.
Yeah, but there's some interesting things going on. So, for example, you see those 3 fingers from the hand. What you don't see is a big lump from the base of the 4th finger, the wing finger, which is massive, of course, and really fat and kind of sticks out. And it suggests that that is somehow lifted off the ground fully when they're walking on their fingers, which is actually slightly odd architecturally in terms of how the bones would have to sit. But even when they're quite deep and pushed into the sediment, you can't see a trace of it. So that's just they're really kind of pushing their fingers like out and free of the rest of the hand.
A bit like the way that obviously they're not walking on their knuckles, but a bit like a way a gorilla will walk on its knuckles rather than walking with its
so they're really quite good at it in the way that, for example, for like theropods, when they sink into admittedly very deep mud, you then get like the 3 toes and then this kind of extension off the back, because you can see where not quite the heel, but the base of that palm is going in. And pterosaurs just don't seem to do that.
Don't want to get their wings dirty.
No, apparently not, but they're really quite good at it. And so that's how they're walking. A lot of them are probably pacing, so doing what giraffes do, or greyhounds and cheetahs, so the 2 limbs on the same side moving together. It's a fairly obvious thing to do when you've got relatively long limbs and a relatively short body. You don't want to be kicking your own ankles. And they're probably quite good at it. I mean, the thing is, pterosaurs are nice and light, even the very big ones. So actually, they're not leaving many footprints unless we've got, really nice, fine, muddy stuff that's going to preserve well. So it's perhaps not a big surprise that when we do find tracks, they're either really big asdarchids because they're nice, relatively big and heavy, or they're small ctenocasmatids because they're pattering about on mud flats, filter feeding and probing and grabbing, and not a lot else in between. But that kind of makes sense. Again, where are we going to find Pteranodon footprints? This is an animal that we think lives on the cliffs up to the point that it takes off and flies around for 1,000 miles across the ocean and comes back to the cliff. Footprints probably not turning up anytime soon. Yeah, we do have a ton of pterosaur footprints, but they're very, very restricted to what groups they're from, and they're also then very, very restricted to what kind of activities they're doing. But I think most people would agree that the pterodactyloids, at least, are probably pretty active, pretty capable on the ground. They could run, they could jump, they could dodge and turn a bit. They're not clumsy.
They do have very, very large heads, though. And I know they're not heavy heads, but surely that's got to get in the way of like stopping your beak from hitting the ground, and stopping
yes,
looking around, and I don't know.
It's probably not ideal, but again, compared to, I think, a common perception that they're just kind of flopping around and barely capable of walking in, even the better ones. Well, with the very leggy ones, well, they walk very well, but they're like giraffes. They just walk very well, and then when they run, they're rather ungainly and they can't really do anything else. I just don't think that's the case for the vast majority of them. It's going to vary enormously. Ctenocasmatids have got really big flat feet, probably with all that webbing on them as well. That's not really what they're built for, but certainly some of the smaller, more terrestrial derived pterosaur pterosaurs are probably really pretty good on the ground in exactly the same way that things like Mystacina and vampires are. There's been some selection for being good terrestrially, and they're good terrestrially.
Is there any evidence of them climbing?
That's where I was going to go into a minute. First of all, to deal with the non-pterodactyloids. So what about them with their legs all stuck together? Well, there's an obvious, and again, the absence of tracks, so there's this obvious suggestion that they basically rarely came down to the ground. Now, they've got to be on the ground inverted commas somewhere, whether that's a cliff or a tree, or, they're not just flying 24/7, they're going somewhere, but presumably, rather like most bats, as you kind of suggested, they're not very good on the ground, and therefore they are in trees and cliffs, and therefore no footprints. And we didn't have any at all until 2 or 3 years ago, and one set of tracks at Chrysac has now turned up, and it's very clearly a Ramforinkus-like animal. It's got different orientation of its fingers. They point forwards, not sideways and back. And there's an impression of part of the long fifth toe. So clearly they
got their wings muddy.
At least one came down and was walking around a bit. But if anything, that only kind of really emphasises that general point that they're clearly not doing this much. On the other hand, if we think they're mostly catching their food on the wing and stuff like this, well, why would they come down and paddle around in the mud? If that's not how they feed and that's not where they need to be, then they're probably not going to do it. Whether or not they were any good on the ground, regardless, has been another big question. So the idea that, again, tying all the membranes together probably kind of ruined your terrestrial ability, that has very much stuck. But Mark Whitten did a paper, God, again, Dave's memory of times when things happen, particularly post-COVID. 5-6 years ago, something like that, wrote a really quite big and in-depth review and kind of synthesis of all the data on how they might locomote on the ground. And he argued pretty convincingly that actually they're probably quite good in terms of things like running around on tree branches and even running around on the ground. They may not have been great, but a lot better than people think, where they think of them as being like your average bat, where they're kind of stumbling along and just crawling until they can get to a tree and climb up it, and then they can fly again, and then they're fine. Particularly Dimorphodon, which people had suggested was generalized predator of small animals and has pretty robust arms and legs. That is increasingly looking like an animal which probably was pretty good on the ground, or in particular, maybe motoring around the trees. And yeah, a lot of these almost certainly were hanging around in trees. Now, here is something, if someone knows different, and I know at least a couple of my colleagues listen to this podcast, if anyone knows different to this, please tell me. If there is one thing that bugs me about pterosaurs, well, there's many things that bug me about pterosaurs, but if there's one thing that really bugs me about pterosaurs, it's the massive discrepancy between the claws on their forelimbs and the claws on their hind limbs. So those 3 free fingers have usually really pretty big claws on them. They're pretty curved, they're pretty sharp, they're pretty strong. They often have the deep ligamentous pits behind them that we've talked about, and even little bones called sesamoids in those pits to give you an even stronger
grip
ligament. So in other words, they've got really big, strong grip. And then their feet have weedy little blunt claws. Now, on the one hand, okay, we said, these are front arm flyers, they're front arm launchers. The legs are actually pretty weedy and don't do very much.
They skip leg day, Dave.
Yeah, they're almost there for support. And it's like, on the one hand, that kind of makes sense. But on the other hand, for those that are hanging around in trees, and we think a whole bunch of them were, and including actually some of the derived Ashdarchoids, so ones that are close to Quetzalcoatlus but not quite, including Tapiaras, which you mentioned before, so maybe eating fruit and nuts and getting up into trees. Big claws on the hands, almost nothing on the feet. Okay, so the hands have got most of the muscle, and if they're poking about in trees, big strong arms, big strong clawed fingers going up and down a tree, makes sense. But their feet have got to do something. They're not just hanging in space or flopping around.
Why not?
You would think some better claws on the feet would really help.
I've seen perfectly capable, professional climbers just climb up walls only using their arms, and they're much heavier, and they can hang from one hand and do other things.
They are, but capable of doing something and are selected to doing something are not the same thing. If they're not using their feet at all, I'd expect the feet to get even smaller and the claws to vanish.
But unless they're walking around as well, in which case they need...
Well, but at least a handful do have big toe claws. So there's a couple of them out there, but most of them don't, and including things like Anuregnathids, which we're not going to talk about now because we're going to do an episode on Anuregnathids. We think they're basically living and hiding in trees almost their entire lives, and yet toe claws are pathetic.
It's normal in things like, and cats do use their back legs a lot in climbing, because they obviously jump up to get up there and everything, but their back feet are not got those same grippy claws that their front claws do.
Yes, but they're still much better than we're talking about for these pterosaurs.
Yeah, but it's an example of even animals which are definitely using their back legs do not have that adaptation in their back legs.
Yeah, but if you look at properly arboreal animals, though, animals which really are adapted to living in trees, it's usually rather better. And so it is a surprise that they're like that. And the flip side of that is you've got some Ctenacasmatids and things like this, which we think are, and even Pteranodon, that are mostly, hanging around the water's edge and stuff like this. And they have pretty big claws on their hands, which, like, they're not climbing at all. So why do they still keep them?
Maybe they arm wrestle.
It is an odd combination, and it's something that I think needs really looking at.
Could they be also used for feeding their claws? Are they using their...
Nah, they're too far out, and they don't have the arm flexion. Just to say about climbing then, people have suggested at times that they probably wouldn't be very good in trees because you've got these dirty great wings, which, they will fold up alongside the body, but are still going to stick out a lot more than birds' wings would. And then again, lots of them have got big head crests, particularly things like the tapiarids. I mean, if you look at the average big tapiarid, 2-3 meter wingspan animal with a giant head crest and pretty big wings, it doesn't look like the kind of animal that would be capable of clambering around branches very effectively. It's got too many odd bits sticking out, and yet it looks like it probably did. There are some odd combinations of features.
Were the trees different? Are we talking about, because it could hang around palm trees and just climb up and just sit on the top of a palm tree and be quite happy.
Not sure it's eating coconuts though.
No, but it could just hang out there.
Yeah, but you can't rely on a homogeneous landscape in which to sit in a tree. That doesn't work across, I think 30 million years and half a dozen continents.
We need to know the type of tree, Dave. That's what we need to know.
I'm terribly sorry. Anyway, the short version is pterosaurs are pretty good on the ground. Even the Ramforinkoids or non-pterodactyloids were probably pretty good on the ground. At least a bunch of them were getting into the trees. Exactly how good any of them were, but better than I think a lot of people think.
Okay, so now let's go to Splashy Splash. Are they a flappy flap splashy splash? Could they go underwater? Could they dive? Could they dive, Dave?
So yeah, these are some big questions. Undoubtedly, some pterosaurs are hitting the water and need to get out of it again. Like specimens of Pteranodon found like 150 kilometres off the paleo coastline. If you hit the water and just die instantly, that's probably not very selective. Though, as I pointed out in a paper, so some of the tropic birds apparently can't usually take off from the water. These are oceanic-going birds, which if they hit the surface, drown and die. Evolution does do some weird things when it comes to ecology like that.
Don't drown and die. It's fine.
Yes. In general, though, as we said, they could probably take off from water fine. The question is quite what are they doing, when they get there and how well can they get around? So I did a paper a few years ago with Don Henderson, who I'm sure we've mentioned before because he does these wonderful 3D models and looks at buoyancy. Yes, we talked about it for Spinosaurus and his models of tipping and other things. And Don and I did this paper on pterosaurs because I worried about, not that they're buoyant because they're so pneumatic, they're obviously very buoyant. They're going to fly really high on the water's surface, but where are different bits of them going to sit? Because the body is actually a lot more pneumatic than the head, which means you run the risk of the body sits proud of the water and the head's half under the surface. And it wasn't quite that bad, but we did find that, they don't sit like ducks. They can't retract and fold their neck in the way that ducks and geese can. So if pterosaurs sat and floated on the surface, the head is basically stuck out in front of the body and is sat on the surface of the water, which is pretty suboptimal when there's waves and splashing going around if your nose and mouth are, millimeters off the surface of the ocean.
I just had an amazing thought, which you'll be wrong, right? But the amazing crests, the ridiculous crests. Is it possible that those are
not
pneumatic? Oh.
No, they're not connected to the nose.
Oh, that would have been amazing snorkeling.
No, they don't have snorkels. Well, that was argued for Parasaurolophus for a long time. But anyway, so we argued from that that pterosaurs probably don't want to get caught on the water surface very much. They're not like ducks or gulls or albatross or things like that, which if the weather gets really bad, or if they screw something up, or if they've been swimming or diving and they're stuck on the surface, that, you know, they'll just sit there and, you know, just bob up and down in the waves and wait for it to go. We think that's probably bad for pterosaurs. So we suggested as a result of this that probably really want to take off again pretty soon after doing it. As a result of that, since I'm soapboxing briefly, so that paper's now been cited like about 20 times, and I recently looked through them for some reason. I think because I'd spotted one, so I went through, and of like the 20 papers that cited it, about 15 said that we said that pterosaurs couldn't swim, when that's not what the paper's about, and we specifically say they could swim. And then a couple of the others said that pterosaurs float very low in the water, and that's why they drown. And we didn't say that. We said they float very high on the water because they're incredibly pneumatic. It's just that their head points down, not up. So almost every citation that cited that paper has said the opposite of what we said, which is slightly worrying.
Well, you should write your abstract better, shouldn't you? Because that's the only bit that people are reading.
People read, yeah, I should read the paper better. Even the abstract says, and they could swim. Well, as I say, we, as in me and Don, I think a number of people think we're probably right. But I didn't mean we as scientists. We think they're probably not very good on the surface. That doesn't mean that they're not swimming. And there are putative pterosaur swim tracks. And these are actually rather like the dinosaur swim tracks that we see, where, of course, they're not actually quite swimming, because otherwise their feet wouldn't be hitting the bottom. But you can see sets of scrapes of 4 little toes in pairs, which is what you'd think from their feet paddling along and hitting the bottom and scratching a bit through the mud. And I think those are quite plausible. But again, that doesn't mean they're necessarily particularly good at it. The wing membrane is going to be connected to the legs, even in the pterodactyloids. So you're going to get an awful lot of drag from trying to paddle your legs around with the wing membrane flapping about.
But that could counterbalance because, you've got the drag going the other way as well. So when you're pushing, it would act like, extra.
Yes, but you're going to get a lot more going forward. It's really going to slow. And remember, the legs aren't that well muscled, so it's probably more of a hindrance than a help. So I suspect they could paddle about badly. So I saw a pigeon got trapped in fell into a canal once, and you watch it, and it's kind of desperately trying to do like a flying action with its wings while its legs move. And it was going through the water. And if an animal is moving itself through the water, it is swimming. Was it any good? No, it was absolutely rotten, and it nearly exhausted itself going 10 yards. But I think pterosaurs are a bit better than that when it comes to swimming. But the idea that they're paddling about like ducks, which you will see out there, I think for most of them that's probably not the case.
But they're not,
even when they've got relatively big feet with webbing, as we talked about last time, because that can just be linked to sitting in mud.
But they're not flying underwater like penguins.
Well, or more specifically, things like orcs.
Yeah.
Things like razorbills and puffins and various other stuff do that. So Jurassic World, the first one, actually showed this quite well. The big pterosaur escape and the pteranodons, they had them shooting in like pelicans and other things underwater and then flapping around a bit. That's been suggested at various times. The diving bit, I'm not too convinced, but I can imagine they did it.
They've got pointy beaks, heavy heads.
Yeah, but they're also much more pneumatic than a lot of those other animals. They can't fold their wings as tightly to the body, which means they're going to have a lot more drag when they hit the surface. Head crests again in a lot of them. So maybe, certainly if it was like just below the surface, maybe. But when you see them doing like, orc or puffin like flapping underwater, I can't imagine it. The wings are so long, they're not that strong. The bones will disarticulate. They can't really flap with just the bit of the wing and then the wings tucked up. They'd have so much drag. I think they'd be awful at it. They could try, but I don't think it's going to ever get them anywhere.
So how are they catching and eating fish then?
So mostly what they're probably doing is what we'd call gleaning. So taking stuff at or just below the surface.
So they're getting really close to the top of the water, which explains why their face is so big.
There's loads of stuff that does this now. So you'll often see, again, this is another one, you'll see that pterosaurs were skimmers. Skimmers are a very specialised bird where they fly with just the tip of the jaw under the water, and then when it hits something, they snap the jaw shut. Pterosaurs can't do that for lots of different reasons, biggest one of which is their heads would shatter if they tried it. What they could do, though, there's lots of videos you can see big birds doing this. You know, things like osprey are doing it with their feet, and various fishing bats do it with their feet, but there's various birds that will do it with their heads as well. There are loads of fish and squid and things like this up near the surface or just below, and they'll fly along, and just, dip the head in, slap it down, grab something. The head is then kind of pulled along under the body for a second before they can flick it back up. But they'll grab stuff like that. I think a lot of them are grabbing stuff in that way, or diving, but as in just getting under the, they might have been quite high initially, but, they're hitting the surface and they're only going down a metre or so, and then they're turning around and very awkwardly flapping or coming up to the surface. They're highly pneumatic. They'll bob up anyway pretty quickly, swallow whatever it is they've just caught, take off, go for another one. I think for at least the oceanic stuff, I think that's what most of them are doing.
This doesn't sound overly elegant, Dave.
Probably not, but it doesn't have to be. Look at pelicans. It only needs to be effective.
Yeah.
And animals do weird things. If you watch some of the fishing bats or the frog-eating bats, fishing bats in particular, because they'll trawl with their feet. And so they'll be holding their feet under the body and they'll stick it under the surface and grab something. They will often loop the loop as a result of this, because there's quite high drag on the feet already, and then they've hit something quite heavy, and they're bats, so they don't weigh very much. And that weight basically pulls their head down, and they flick their legs out, and the legs go all the way over the head. They're now free of the water, and then they fly off.
Genius.
You can watch videos of this. I'm not exaggerating. So weird things happen when it comes to this, provided it works. So could they swim? Sort of a bit, probably not very well. Could they fly underwater? Almost certainly not. Or if they could, it was very bad at it. They did float.
They wouldn't do what a daddy longlegs did to me once when I was in the bath.
I'm intrigued to know where this is going.
So I was in the bath, and a daddy longlegs. What's the scientific name for a daddy longlegs? Harvestman? Is that?
So are we talking about harvestable
flying.
arachnids or the flying ones?
Flying.
They're crane flies.
So a crane fly came in through the window, and like all crane flies, it aimed for my face.
I thought you meant it just flew in random directions.
They're basically drunk men. They're gonna once they enter the room, they're gonna try and touch your face. That is their golden life. They're very sweet. It came in, and then it kind of went for my face, so I sort of dodged out the way, and then it did the most amazing thing, which it dived into the bath, and when it hit the water, all its legs fell off.
Yeah.
So they're a bit more robust than that.
They are, but I think if Pteranodon really tried a deep spearing dive from like 15, 20 metres up, that might well be what happened. There is at least, so there's two Brazilian pterosaurs like this which are relevant. So one has a leaf trapped down the lower jaw, so like inside the lower jaw and then poking through the bottom. That's nasty serrated leaf. And the interpretation of this is that this leaf sitting around on the surface looks a lot like a fish. We know exactly of pelicans that do the same thing now, where they see something like that and grab it, and then this nasty serration gets like stuck in the tissue. They don't have a mobile tongue, they can't get their hands in the mouth, and they're now just stuck with something jammed in their mouth that means they can't close the mouth properly, and they just starve and die. And we have a pterosaur with that, it's a thing called Ludodactylus.
Ooh, that's the finger. Somebody. It was Steve who understood Ludodactylus and what it meant. Something finger. Ludo. What did that mean? Oh, I can't remember. That's annoying.
What is Ludo? What would you normally do?
Oh, it's like Cluedo, but I've lost the C.
It's a board game, Ludo.
Yeah.
But Ludo, it means play. It's play finger, and so because it's a toy. And the reason for this is Ludodactylus is ornithocheiroid pterosaur, so one with a long snout full of teeth, but also has a pteranodon-like crest on it. And the kind of joke is that like all the crap toy manufacturers, that's how they'd make pteranodon. They'd give it a crest and then they'd give it loads of fangs at the front because it's a dinosaur, so it's got to have fangs if it's going to be a toy. And it's like, no, there's actually a pterosaur that looks like those rubbish pterosaur models, which are bad pterosaur model. So that's the joke, is it's the toy pterosaur. So Ludodactylus has that. And then the other one, and I can't remember which one it was now. I want to say it's a thalassodromine. Someone will know and remind us in comments somewhere, I'm sure. But basically, it's got like a shattered lower jaw. And it isn't just shattered, it's like pushed in on itself. And about the only way you can pretty much... And this is, again, an animal buried in a lagoonal system. About the only way you can realistically do that is if you hit something very hard end on.
Bruce Lee kicked it.
Well, the interpretation was something not dissimilar. There's a buried log or a hidden rock or something below the surface, and it sees the thing that it's going for and just walloped it and
stupid pterosaur
smashed its face in, but both of these are a bit speculative based on limited data, but they're also perfectly plausible. We know living animals that fall foul of these exact accidents, and it's hard to explain away how they did this otherwise. So yeah, that's what we think happened. And both of those point to grabbing fish and things at or just below the surface if you're picking up those kinds of stuff.
That makes sense. So you know how it happens because they mucked up.
Yeah,
that's
basically.
Great. I like that. You can explain a lot of my life by what I get wrong.
And the injuries.
Pretty much. Oh.
So pterosaurs could fly very well. Pterosaurs were probably pretty good on the ground and better than most people realise. Pterosaurs mostly probably weren't good in the water, but were doing okay in the grand scheme of things.
Yeah, they were a bit like umbrellas.
Ramforinkoids on the ground have been described as broken umbrellas blowing down the street, which, again, is probably a bit harsh these days from off the back of Mark's paper, but also is probably not that badly wrong either.
And finally, we should just say, for the flying and the back toes and everything else, because it is a point that you often make, is when they were flying, they probably weren't carrying things in their limbs.
No, the fingers don't grip like that, and the feet are not shaped to curl them up. So yes, the classic 1 million years BC, or all the way through to Jurassic World, 50 years later, or picking people up with their feet and flying off, or anything else for that matter. No,
they'd pick you up with their heads, and they wouldn't pick you up because you're too heavy. Get a grip.
Yeah,
exactly. Cool.
Yeah, I mean Jurassic World with pteranodons picking people up who are heavier than them. No.
Yeah. I mean, they could still squawk at you, and I think that's scary enough.
I mean, I wouldn't want to fight one, and as in actually Jurassic Park 3, where they come across a big male pteranodon on the ground. Yeah, the thing's massive. It's head height to a human with a metre-long spear of a beak on its head. Yeah, I would not want to fight one of them, but I wouldn't be too worried about one flying down at me.
They're just pointy faces. They're not beaks.
Well, in Pteranodon, at least, it would have a proper keratinous sheath. It would absolutely be a stalk-like speary beak.
Excellent. Well then, ladies and gentlemen, boys and girls, I hope to enjoy how your flappy flaps get around. They're very good in the rain, obviously. So you can stay underneath a Pteranodon in the rain is probably the best place to be in the Cretaceous. But apart from that, we will say thank you very much to all our patrons. You are magical people. Please join us on patreon.com/terrible lizards. Find us on the Twitters. It is at Dave_Hone. That's HONE. You can find Dave. You can find me at ISZI_LAWRENCE. Oh yeah, just say hey on Patreon. Other than that, until next week, we've got to do a pterosaur squawk day. So don't look scared. I'm going to do it, but it'll be okay.
Take the headphones off now.
After 3, 1, 2, 3. See, it wasn't too bad this week. It was nice. Thank you for downloading this episode of Terrible Lizards. To support us, please become a patron on patreon.com/Terrible Lizards. If you can't do that, don't worry. Just leave us an amazing review on your podcast app. Also, you can check us out on Twitter. I am ISZI_LAWRENCE, and Dave is DAVE_HONE. You can also check out our books. Dave's got a load of dinosaur ones. I've got a load of children's ones. I also do other podcasts as well. Go to ISZI.com. If you have dinosaur questions, you're going to want to email terriblelizardspod@gmail.com. That way we can answer them in the questions episode. I think that's all I have time to tell you, but thank you if you support the show already. You are amazing. We will see you next time.